Good morning, everyone. Welcome to our next lecture, lecture number 8. And today we are going to speak about ferromagnetic resonance or ferromagnetic resonance spectroscopy. So the plan is to discuss a bit hardware, then how do we define saturation magnetization and anisotropy constants in the thin magnetic film, and then how to define Gilbert damping parameters and inhomogeneous linewidth broadening. So the lecture will be prepared, so I will use also Blackboard today, and I will try to give you simply advices at the very end from practical perspective to what you should pay attention if you start doing ferromagnetic resonance measurements. So, what is FMR? As we discussed, and we have seen this nice animation of Rostislav Sirha. So when you have magnetization, you apply field perpendicular to this M, you will excite magnetization precession, like it's shown here. And if all your spins are excited in phase, like it was shown here, then we are speaking about ferromagnetic resonance. Or you can describe ferromagnetic resonance as a Magnon spin wave with k equals 0, namely with wavelengths equal infinity. So very big wavelengths, and we are speaking about ferromagnetic resonance. So this is physical phenomena, but resonance people usually FMR refer to it not really like phenomena, but more like to technique, which is used to characterize a magnetic material. Because performing ferromagnetic resonance, you can collect a lot of information about your magnetic medium, about your sample, and about your material. How do we perform for FMR? First of all, you of course need a hardware, and first of all you need to apply this biasing magnetic field, like shown here, B0, and for this we use magnet. Yeah, so there are different magnets people are using, smaller, larger, some of them are 2.5 tones, which gives you very uniform field in a big volume. We use this magnet from GMW, which is 600 kilo around, and yeah, so it has a power supply, water cooled, and it has magnet control, which keeps the field constant. We have other components, and very important here is a vector network analyzer. So this is a device which sends you information to your microstrip line there, to your sample, and performs principally measurement. So, but before we go to VNA, let me say a few words about magnets. So principally important issue in FMR is uniformity of magnetic field. Sometimes it's more critical, sometimes less critical, and usually what we do, we perform such a very simple calibration when you just put some hole probe into fix it with you fix it with some screws, step motors or so, and then you can perform measurements of magnetic field versus coordinate in all 3 axes. And principally, the more uniform field you have in your magnet, the better. Therefore, what we are trying to do in practice, we are trying to take magnet with as large as possible pole of magnets. So this one, I think, is 12 centimeters or so, and there are bigger. And this is first what you do, and second, you are trying to find to decrease spacing between poles as much as possible, because the smaller the spacing, the more uniform field is. In your case, in some cases it's more important, in some cases it's less important. But keep in mind that you want to find such a holder, design such a holder that your spacing is smallest. So we performed measurements of internal field. Then what do we put in? We put our sample, and this looks like this microstrip line. So this is just one of the possible designs. So you see here is microstrip line, simply 50 ohm matched. You know what is this? We already discussed basics of microwave technique. So simply a microstrip line which creates field around, which excites magnetization, precession, ferromagnetic resonance in your sample, which is placed here. The sample you see is practically transparent. It means that this is a very thin yttrium iron garnet film, maybe 100 nanometers thick. And then we have to connect this microstrip to two microcoaxial cables. Here use SMA connectors and N-lunge connector, which make more or less contact from this microstrip to coaxial, so one side, another side, and all this is fixed in magnet. And of course, you're trying to make sure that your sample is located in the center of magnetic field, because this is a place where it's the most uniform, so it should be vertically and in this direction, and principally in all three axes, try to put it as close to possible to the center. That's how it looks from the side. This is a strip line, and here is line your sample. Setup is very simple. So it's one of the simplest setup you can do in magnonics, experiments you can do in magnonics, magnet, microstrip line, and vector network analyzer. And what vector network and your sample. Yeah, what vector network analyzer measures, it just sends some microwave signal from one port, then from another. It checks how much is reflected, so it measures S11 parameters, and how much is reflected from other side, S22 parameter. It measures transmission from 1 to 2, so S21 parameter, and it measures transmission S1 to transmission this side. And it measures all this as a function of frequency. So you define that I want to measure it from 5 to 10 gigahertz, for example, with a step of 1 megahertz. And then vector network analyzer does all the job for you. So we use this AG length in the frequency range up to 20 gigahertz here. In the case of need, we move up to 40 gigahertz with another setup, and maximum what we can measure is 70 gigahertz with a third VNA. Yes, please.
Just for clarification, the strip line is continuous. It goes through this. It's one strip line, not
yes.
two.
Just one strip line, yeah. So you connect it from one side and from another, and you measure what is transmitted through and what is reflected. In some cases, people need to do angle resolution. And for example, if you work with cubic crystal and you want to define crystallographic constants, you can do this using ferromagnetic resonance. For this, you need to turn your sample, crystallographic axis of sample with respect to the applied magnetic field. And the easiest way, the straightforward way, how one of the students did this one in Kaiserslautern. Just print it on printer, this scale, and then you can use some angle edge of your sample, and principally such roughest measurements you can do just turn in sample. Not probably the best way, but principally in many cases it gives you what is needed. Of course, there are many experts in FMR who have special rotational stages and so on, which perform, but keep in mind that when you rotate something, it's very important that your sample is located at the same position, because if field is non-uniform, and even in this big magnet with such small spacing, there is non-uniformity. If you will start rotating your sample, if it's not at the axis of rotation and it will move slightly out, then you will measure more or less your change in the bias in magnetic field rather than crystallographic anisotropy. Yes?
But on this PCB, the vertical antennas, they are just there to see in which angle I am.
This is section from another experiment. They are not in use in this one, so what is used in experiment only this U-shaped antenna, and this is used for inverse pinhole voltage measurements. So when you have yttrium iron garnet with platinum, you put it here, you connect it platinum here we just put ground, and then you, using this SMA, you simply measure DC voltage created by spin pumping and inverse pinhole effect. Yeah, so this is just here because we had such a sample. Okay, so what do we actually measure? How I usually explain FMR, idea is very simple. So you see here is shown absorption as a function of frequencies. So you have VNA, you install some fixed frequency, that your FMR frequency around here, 7.7 something gigahertz, and field is fixed. and you have such a microstrip. What do you measure in reality? You measure S21 parameter. So this is frequency. Here I assume that my FMR, frequency of resonance, and then I measure S21. If I'm staying far away from the ferromagnetic resonance, far away in terms of frequency, then sample does not influence my transmission much. There will be some small reflection from this side because it changes the electric constant of YIG and GGG substrate is different from air, so there will be small reflection, but in the rest you won't see much. So here, if you will then put, I don't know, let's put it in dB, yeah? Like it's usually measured. 0, it means this is everything goes through. 0 dB means 1 in a ratio, in intensity ratio, power ratio. You will see something a bit smaller depending how you calibrated your setup. If you're staying far away from frequency. If you are staying on the other side, far away from FMR, principally you also see the same transmissions that everything goes through. The story is getting interesting when you are coming close to the ferromagnetic resonance frequency, because what happens now, this field excites magnetization precession, and as soon as you excite magnetization precession, it means you spend energy for something. It means that energy which goes through will be decreased, and here you will get such a resonance peak like Lorentz. So it means that here you will have some absorption of your microwave signal, and that's what you need principally in order to perform. So this is already a ferromagnetic resonance measurement. So this width, as any resonance curves, defines a damping. So at the end of the day, you will get here damping, and this position FMR will give you information about, so this is Gilbert damping parameter alpha. And this one will give you information about saturation magnetization of your film and different anisotropy constants if you will perform these measurements for different angles of magnetization. So that's how we do it. This type of measurements is named broadband ferromagnetic resonance frequency. Broadband because you can perform this for different frequencies. So for one field you have FMR here, you change for around 7 gigahertz, here you decrease field, you will have it at 5 gigahertz, you increase field, you will have it at 10 gigahertz. And principally, if you want to measure alpha properly, you need to scan in a broad range of frequencies. The broader the better. Then you should be able to have nice linear slope, and you will determine your alpha with high accuracy. And because you are able to work with any field at any frequency, it's named broadband, and majority of experiments done nowadays are done like this. In the past, classical ferromagnetic resonance was done differently. People used cavity. So you remember our waveguides, these rectangular waveguides. So more or less you just take part of that waveguides and add 2 balls in there. So there will be some field distribution. There was some trick how you couple this cavity to coaxial cable, for example. You put your sample somewhere in the middle, and then you magnetize it. Yeah? And this is classical ferromagnetic resonance measurements, which was done before. What is trick here is that you need to have a cavity with high Q factor. So Q factor is a ratio of resonance frequency of your resonator to the line width. So more or less, like if to analyze with FMR, this one normalized by delta. And Q factor should be very a lot of, so several thousands, let's say. And the trick here is that resonator has fixed frequency. It means that you are not able to tune frequency like it's shown here. Instead, what people did in the past, they measured always, for example, again, some absorption, somehow recalculated as a function of field. So frequency was constant, and they measured it as a function of field, and they have seen also some absorption. It means that this technique is very sensitive, very nice, but it won't give you all information about alpha. It will give you just line width at one single point. Therefore, nowadays, and it's a bit more complex than a simple broadband strip line FMR. Therefore, now people are using it less. But what is good, of course, about this technique that here, for example, you can always modulate this field. You can make it H plus delta H in some kilohertz frequency range, so you can use so-called lock-in technique. So if you want to perform super sensitive measurements, usually lock-in technique is used, and classically people perform this experiment with minor modulation of field at some frequency, let's say 100 kilohertz, and then they measured feedback at 100 kilohertz frequency, which allowed to increase sensitivity of the setup. Yeah, so that's how it was in the past, but we will focus today on this approach, which is more commonly used. And then what you can do, yeah, so we're probably asking how deep is this absorption? It really depends on the size of the sample, how large is your sample, so what is the volume of magnetic material that interacts with the field of antenna. And first of all, thickness is critical. Yeah. So if it's some thick sample, like 5 micron thick yick or so, then you can expect here, I don't know, maybe 5 dB. Quite big absorption. Sometimes 10 dB. If you try hard, you can really have it as absorbers. That's people think into. We're designing stop band filters based on this approach. If you're working with nanometer thick yick, then this will be maybe for the 0.1 dB. Very, very small signal, which you will hardly see in the, without subtraction of reference signal. Therefore, be always careful how large is this absorption. And then what you can do afterwards, when you have simply S21 parameter, and you can just, in the simplest case, what you can do, you can just subtract this. If this is a maximal absorption, you can normalize this to 1, or here just some arbitrary unit, so more or less you need to invert it in order to measure absorption, or 0 minus this one. But be careful, yeah, if you are working in dB scale or in ratio scale, so you need to divide one by another. And then what you will be able, from this S21 absorption, you will be able to plot absorption in arbitrary units as a function of frequency, which you then fit with something. So we will discuss now with what to fit. Yes?
Is it more usual to plot it like this? Or is it also fine to plot it with power ratio, for example, when you publish?
No, people usually plot this kind of graph. This one usually, because this is just technical details, how good is calibrated, everything. So what's important is really absorption. And I would not plot it in dB, because for fitting, usually it's already, it's not in logarithmic scale. That's what we also discussed last time. Please be careful, always do not use, because sometimes people might make this mistake that they take value from as a vector network analyzer in dB, they invert it and they fit it with linear function. Yeah, so it's not correct. Although when values are very small, for thin films you might be not necessarily see much difference, but strictly speaking, keep in mind always if you are in work in logarithmic scale or in ratio scale. So how to fit it? We discussed ferromagnetic resonance story, and here is a book of from this chapter written by Carl Patton about microresonance and relaxation from Colorado State University, one of the classical people in the field. And he shows this is susceptibility, which we also discussed earlier. And here you see that there are such two components where then omega minus omega squared and eta 0 is more or less damping parameter. But here there is also another term where omega plus omega. And here at the bottom I show you the Cauchy distribution or Lorentz function more or less, which we use to fit. And you see that principally the second term is not here in standard Lorentz. And but at the same time you see that if you have this, instead of minus, this will be very small. Yes, this will be close to 0 at this will be 0 at the resonance point, and this value will be very large because this is omega, and omega plus square, and it's squared. So principally, in majority of the cases, people ignore the second component and just you can use some, in the easiest case, Lorentz. We'll discuss other tricks. Sometimes this curve is not really Lorentz; it has some more complicated shape. We'll discuss how it's done, but my message here is that you can just use Lorentz, and then you will get your value. Again, pay attention, what are you measuring? What is this gamma? Yeah, when we discuss damping, I especially devoted one slide or so on different types of damping. Omega 2 prime, yeah, imaginary part of frequency, lifetime, full width half maximum. And there is half width, half maximum. So be careful what is measured and what is here, because it's very easy to lose two here. Therefore, check what will be your gamma. If you perform these measurements, and pretty often people put here not absorption, but something like dA over dH, derivative of this one. Then when you measure derivatives, then your curve will look like this one. It will be like asymmetric component. And then also pay attention that usually people, what they do in experiment, they just take this distance between these two peaks. But this distance is not full width half maximum. It's not this gamma. So there will be some factor square root of 2 or something, so there will be some additional factor which you need to take into account to recalculate your width properly. Good. And now I would like to focus on the anisotropy. So we discussed anisotropy, and one of the ways you can subtract it is to perform ferromagnetic resonance. So this is again this paper of Bircher et al. And Chris Levchenko made this part detailed supplementary materials where all these formulas are placed. Formulas are not new, as I said, they were given used already by people. So she just made it more or less systematic studies of everything. So we hope it will be easy for beginners to find out. And there, at the end of the day, you have two types of formulas for GGG or for any other cubic crystal growing on 111 substrate. So here are all these axes shown, or growing on 001 substrate. And then you have here ferromagnetic resonance frequency when it's magnetized perpendicularly, and here's uniaxial 1, uniaxial 2 anisotropy, and cubic anisotropy HC. The same for this one. Formulas are slightly different. And then when you magnetize it in plane, there will be two formulas here, depending if you magnetize it along 1 minus 1, 0, then it will be this formula. And if you magnetize it 1, 1 minus 2, this axis, then there will be another formula. And here it's a bit easier, so it's 1, 0, 0, it's along just perpendicular sum of the axis. This one will be this formula, but you also can, so when you turn it 90 degree here, so here it's 90 degree difference between these two axes is 90 degree, because then something changes. When you have this configuration, 001 substrate, turn on the 90 degree changes nothing, because you have this symmetry. Therefore, here's this formula. This is more or less along one axis, and this is a diagonal. So you need to turn here sample by 45 degrees, and then you will be able to see your magnetization. To measure your magnetization, you will be able to subtract this cubic anisotropy constants. So you see here there are many, these three more or less anisotropy constants. Also in this paper you will find a algorithm how you can subtract it, developed by Professor Zavisilak from Kyiv University. Good. So that's what so much about formula and theoretical background. Let's come back to the practical side. And here you see just some given without any special search, just some YIG, and this is resonance frequency as a function of applied magnetic field. So for each applied magnetic field you have this peak and you define this FMR, and this is resonance frequency plotted here, and you see such behavior. And people always name it simply Kittel fit. So this is because it's based on Kittel function, and from this Kittel fit, you are principally obtaining, or this is Kittel plus anisotropy. That's one of these equations you are using to fit, and maybe you need to measure for several different angles. But what you will get out of there, first of all, it's magnetization. Yeah, it's large components of this H parallel or H perpendicular. It's applied magnetic field, and MS is usually your unknown. But in addition, of course, you have this smaller components from anisotropy. So you can get then magnetization in this case, if, for example, you ignore crystallographic anisotropy, and you will have such a curve which you can easily fit in origin, for example. The story is a bit more complicated, might be a bit more complicated if you want to get Gilbert damping term. And besides Gilbert damping term, there is so-called inhomogeneous linewidth broadening. Yeah, so again, this Lorentz width, so now we are speaking about gamma, because before we were talking about x minus x0, more or less position of your resonance peak. And now the line width. How to define it? Again, these are formulas in the same supplementary materials. Again, nothing new. You will find that everywhere in literature. And but important for us is, yeah, so this formula, and you see this is delta H. It's your ferromagnetic resonance line width, and it's given by some offset, and this is named inhomogeneous line width broadening, plus some component which is proportional to the ferromagnetic resonance frequency. So we discussed that damping, described by Gilbert damping term, is elastic, is viscous. So it means that the higher the frequency, the larger is your damping, the larger is delta H. Therefore, what you need, your curve will look like this one. That's what you plot. Here you have FMR. It's not applied frequency, yeah? It's frequency which you already subtracted from your measurements, ferromagnetic resonance frequency. And on the y-axis you put delta H. It's your width of your peak. And then according to this formula, what you will get, there will be some always error bar, but you will be able to fit it with line. And this offset is named inhomogeneous linewidth broadening. It's more or less property of your sample. Let's say bad samples which are non-uniform have big delta H0. Sometimes it's huge if sample is very bad. But good sample usually grown by liquid phase epitaxy can have quite small delta H0. And the slope here defines your alpha sitting here. And your task in this measurement is really to define alpha, Gilbert damping parameter. Yeah, so that's the main idea. And the first problem which you will meet if you will perform such measurements is that you need to put here delta H as a function of FMR, but in your experiment, when you perform these measurements, there is frequency. It's not field. So it means that you need, first of all, so what you measure in reality is delta F. And you need now to make sure that you are recalculating delta F into delta H properly before you perform such a fit. How to do it? Here is the simplest formula. It's from paper of Calarical, but everybody is using it. that you can, so you see it's delta omega, so 2 pi means that delta omega, and then you just rewrite it in the form delta H, which we are searching for, and then delta F or dF over dH. So more or less you need to take derivative of your dispersion curve, taken here, and you will plug it in. Then there will be some parameter PA, which will be, if I remember right, close to 1, but it will be different. So you need to take into account this additional factor, which is helps you to recalculate delta H into delta F. Usually, so this is a formula, and usually people ignore that this ferromagnetic resonance frequency also depends on frequency. So when you do recalculation, people just use some additional, some formula or simple Kittel without anisotropy. But just if you want to do it super properly, we especially did it in this paper, it stays somewhere in supplementary material. We took this derivative with taking into account anisotropy. So principally, if you want to be very correct, keep in mind that also depending how you magnetize your thin film, you will have different factor to recalculate delta F, delta H, and delta F. Good. And here then just some example of just one of our paper with some handwritten on tablet long time ago. Notice that's how it looks like. For example, you take yttrium iron garnet. It has, so it's liquid phase epitaxy grown by Carsten Dubs in Innovent in Vienna, 2.8, 10 to the power minus 4. It's actually his first 100 nanometer thick YIG. It was his first attempt, but the quality was already much better than we planned. And you see that that's how picture looks like. It really is this delta H already recalculated. When you plot it as a function of ferromagnetic resonance, it's really a line, and it goes to some value around 0.5. So delta H0 was not 0. Why the delta H0 is critical? Because what is the physical meaning? So the smaller precession frequency you have, the smaller damping is. And if you have no precession frequency, F is equal 0, F resonance, principally there should be no damping. So it means that theoretically, this line, delta H versus frequency, should go to 0 in theory. In practice, it's practically never the case. There will be always some offset, and we need to take it into account. And pay attention also that sometimes people report on very small alpha. Alpha is this angle, and when you look on this, it looks very impressive that alpha is very small, but in some cases what happens is that this delta H is simply so large that it stays here, and it's already very flat because damping is given mainly by delta H by some other physical processes. Then you have practically a flat line here with very small alpha, and when you just look on the values, like, wow, cool, great sample, there is practically a very small damping, but in reality, it's only because delta H0 is very large. Therefore, my message here is that at the end of a day, in majority of the cases, for us matters not alpha, but delta H, full delta H at some given frequency, and that is a measure for the damping. But still, of course, when you write paper, so alpha is important. What else you see in this picture is that when you put platinum on top of YIG, then spin pumping will take place, so-called mechanism which increases damping, but also there are other mechanisms, eddy currents, for example, generation, maybe partial proximity effects, that platinum maybe is getting partially magnetic, maybe something else, but it's known that for thin YIG, after you place platinum, material with large spin orbit interaction on top, there will be increase in damping in around 3-4 times, and that's exactly what you see here with this red curve, that damping is increased, particularly in terms of alpha. Yes, so maybe this would be similar or close delta H0, but alpha is increased, so damping in your sample increases. Other questions to that? Yes, please.
I have a question to this slide before. One before. So if I would plot now against delta F, would I get a different slope?
Delta F here on this curve?
Yeah, or would it just shift everything?
No, I think slope will be different because this P is, you multiply delta H on this. So if it would be 0.5, then probably slope will be 2 times different.
But you said before that it's probably, like, yes, it is dependent on the FMR frequency, but mostly you ignore it, no? Or did I understand that correctly?
It depends on FMR frequency, but
no, then I understood it, I think, incorrectly before, because you said you always set it to 1 at some point.
it's close to 1, if I remember right, but I won't be. So the best is really when you perform measurements, just calculate it for yourself, and that would be the best thing, yeah. I don't have here examples, but this is a small parameter which still should be taken into account. Usually error bar you see, so this is kind of a good measurement, but even here you see that error bar is quite large, but in many other papers it may be, in some other cases damping accuracy with which you can define alpha is even worse. And therefore this change delta H, delta F, just necessary to recalculate. It won't change something drastically, but still it has to be done properly. In real experiment, that's what you want to have curve, kind of ideal. This is normalized absorbed power, so this is this paper of Sangeeta Kalarikal, also from group of Carl Patton, which is now intensively used by people doing FMR because they proposed very nice mechanisms how to perform. So there is a little overview of different types of ferromagnetic resonance techniques, but also there is a recipe how to perform measurements, how to analyze data. So that's the ideal absorption which you want to get, and this is a derivative, yes, of such a nice curve. In reality, what you measure can be something like this. This is real part of your susceptibility more or less, and you see it goes here up, then it jumps down, it's not symmetric, it's weird. Or if you take imaginary part of some absorption, it's also not symmetric. It's here one slope, here is different slope, and it goes so slow. And if you start fitting it with nice symmetric Lorentz fit, you will get trouble. So there will be again large error bar. What they have proposed some recipe how to fit. So this is your fit function is given this one, you fit, and the experimental function as these points is abstracted in the following way. So you have here S21, your main parameter, normalized with S21 reference, so divided, and it's all staying under logarithm, and here is again S21 reference. And then with which function you fit it, actually you fit it with this U fit, which gives you some constant, just to normalize some one, again some offset, which shifts everything up and down. And then here stays susceptibility, more or less like we discussed. But what's important here in practice is this phase E I phi, because it more or less gives you opportunity. It switches more or less from the symmetric to asymmetric profile. So sometimes when you perform measurements, you see that your curve looks a bit more symmetric, or sometimes you start getting such behavior like asymmetric, depending on which material you use and so on. Therefore, this phi is of critical, often helps a lot to fit it using this function. Therefore, I just recommend you to try this approach. Of course, keep in mind that if you do it properly, like it's described in the paper, you need to split this function of frequency into real and imaginary part, and then This is also complex value, and you should fit both real and imaginary parts simultaneously. And I think latest versions of Origin already can do it for you. Good. So much about this one. So if you see weird peak, just pay attention. If you will check literature, there are many other papers. So there are many experts in the field which are building different theories. For example, if you have your microstrip line, yeah, here you have some connector, some adapter to coaxial line. And here's coaxial line. Then there will be some sample. So you always will have some reflection here. You will always have some reflection from sample, also from the opposite direction. So there is, I have seen one theory which takes into account more or less all these sizes, phase accumulation in that, reflection parameters and so on. So take into account all four as parameters and with a lot of additional information. But sometimes it works, but in some other cases not. So therefore, just be careful. You can keep in mind that there are more in-depth studies, but from my personal experience, this is something which works good and sufficient for majority of the cases. What else you can subtract from ferromagnetic resonance? Because we discussed damping, magnetization, and anisotropies. In some cases, so this paper was done by Stefan Klinger when he visited lab of Tim Mewis, and he measured this micron thick heat of karst dupes, and he has seen on their ferromagnetic resonance, so Tim Mewis also is one of the leading experts in FMR, they have seen these higher modes, and these are nothing else as higher thickness mode, or PSSV, perpendicular standing spin waves. And the point is, so we discussed PSSV in the past. So if you have a sample, you can get uniform mode, which you usually say just lowest mode or Kittel, but you can have all higher. If it's unpinned, yes, then there will be some second mode, there will be some third mode, and so on. And these modes you can see at the experiment in some cases, like it's shown here. And as we discussed, odd modes are okay. Usually, even modes are less pronounced, and odd modes are better pronounced. But in this case, this is different. Both of them are visible. Maybe because surface of Yig GGG is different than another surface of Yig air. But important for us is that when you have this quantization, here exchange interaction shifts frequency of these modes up. And because this is more or less, you just a standing wave across the thickness. And by this shift, how much it's shifted, you can determine exchange constant or exchange stiffness of your sample. Therefore, what Stefan did, he just, these are the modes, and then when you will plot here so-called exchange field as a function of number mode, so he defined which mode corresponds to which number. And so here again, it wasn't the first paper, just from more recent. There are references, of course, inside to who did it first and so on. But the idea is very simple, that when you plot it by n square, then you will get such a straight line. And from this straight line, you can subtract exchange stiffness. So you can get one more property of your sample using ferromagnetic resonance technique. Other questions? Yes, please.
Can you define which one is the FMR mode and which one are other modes in this case?
You simply try, and so that's the easiest way. So because you see that the distance between these modes is non-equidistant, so distance between second and third is different as between third and fourth. Therefore, you just estimate, you know thickness of your sample, you know approximately exchange constant, and you just say, okay, assume that this is my FMR uniform modes and delta. So absolute value usually is not hard to say something definite because it depends how uniform your field, how in which position you hold sample. But what is gives you a lot of information is distance between modes. Therefore, you just on one side you write measurements that I have such a delta F, delta H in this case, yeah. So much, and then on the other side you calculate, and then immediately, because this delta always increases, you should be able to shift, okay, match. And then you should be able to say, to define the number of these modes. Clear?
Something I could also do for the BPA.
Yes. Yes, you can. So the question was if it's something which you can do for SIG-X. Let's discuss it now. Because I have only one slide left. So as I said, this lecture will be short. But in this slide, instead of writing you, bring in some pictures and so on, I just collected points which you need to take into account when you do FMR. Just some practical advices based on my experience, which if you start doing FMR maybe would be helpful for you to discuss. And we will come here among others to that, David, what you asked. So uniformity of the Bayesian field, check if it's an issue or not. So we had some, in one case, we performed special measurements, a special check, and we have realized that really delta H, so uniformity of the field, changes the FMR line width. The easiest case you can understand it is very simple. If you have some field distribution, for example, so this is coordinate, this is field, yeah, and then, for example, it behaves like this, and your sample has such shape, such size, yeah, is delta X, then it means that here in the middle your resonance field is this one, H1, and here at the edges, even if you place it in the middle, the field will be H2. Therefore, it means that strictly speaking, you could have such a situation that field in the middle. So for H1 you will have FMR here, and for H2 you will have FMR here, and then what you see in experiment, more or less sum of all of them, and you will see one peak like it's shown here, very broad. Yeah, and then it doesn't give information about the damping, but it gives information damping and non-uniformity of the field. Therefore, be careful. At the same time, keep in mind that it's all very important matters with which samples you work. Because sometimes when we take, if our sample, for example, has size 1 centimeter to 1 centimeter, or half centimeter to half centimeter, and your free path, your propagation distance of magnons is of order of 10 micron, or you take permalloy, for example, 1 by 1 centimeter, and free pass is 1 micron only. Then, of course, situation is very different than if you work with micron SIG-X, like David is working, where free pass is also of order of 1 centimeter. Because when it's of order of 1 centimeter, what will happen here, you can have excitation of standing modes. So there will be first mode excited, you can, let's say, second we miss, but third mode can be excited, and so on. And this is possible only if your propagation length is long enough. What does it mean in practice? You have seen this picture where we saw standing modes. These were thickness modes. If you take thick sample, thick means, for example, thickness of YIG, yeah, that's typical material, let's say 5 micrometer. And if your sample will have such sizes of order of centimeter or some millimeters, it means that if you will measure absorption as a function of frequency, you will see many peaks. Most likely in both directions, to the left and to the right. And if you have magnetized it in this direction, H0, then this will be, let's say this is your FMR, and then this will be backward volume waves. How to find these frequencies? Very simple. Oh, I need another whiteboard. Okay, let me. So what are the peaks which you will see? What you do, you just plot. Here's our sample. The size A and B magnetize along field H0 in that direction. And this is our dispersion, omega K, omega FMR. Yeah, so omega means 2 pi F, that you can couple to the previous case. This is your Diamond-Ashbach, this is your backward volume. Oh, okay, let's do it slightly different. Let's do it like this. FMR, usually it has the largest amplitude and it has this frequency. So I will plot here spectrum. So for example, here will be my absorption as a function of omega, and at this frequency there will be large absorption. Now, if I look in this direction of backward volume wave which propagates, or in this case it's standing along the field H0, that means that here the first mode will be when lambda over 2 is equal A. So it means lambda is equal to A and K is equal to pi over 2A equal pi over A. This is by definition 2 pi over lambda. Yeah? So it means that somewhere here will be first mode when I have one standing wave, and this K will be pi over A. Then you have fixed K. It means that you have this omega, and here you can expect your peak. Second one will be 2 pi over A. So you put here, okay, maybe 2 pi you won't be able to excite, but let's say when 3 wavelengths are here, then you will have somewhere 3 pi over A. And you will have modes, and they all at the frequencies below the ferromagnetic resonance. At the same time, you can have quantization over the width. You have here Diamond-Ashbach mode. And here the idea is all the same. There will be some value pi over B, and again there will be then peak here. There will be 3 pi over B, yeah, and then there will be another peak here. And usually the higher the order of mode, the smaller the amplitude. That's why you principally should be able to observe something like this, and the best way, David, as I said, if you want to understand what are these modes, is not to check absolute value, because absolute value, it's really hard to say, because in addition there is always anisotropy. Sometimes we take them into account, but for this you need to perform very sensitive measurements. But absolute value in the theory and experiment may vary, I don't know, 50 Oersted or something easily, which people just associate with anisotropy. So it means that if you measure, you have some given field, you measure some frequency, you compare it to theory, and you see that your FMR is not sitting here but here. Yeah, so this delta you can easily attribute to anisotropy, one of anisotropy components, or simply saturation magnetization. From sample to sample, saturation magnetization can be shifted. So ideal for YIG is 1750, but you can have sample with 1650. Therefore, absolute value, usually you need somehow to find a way, if either it's saturation magnetization or anisotropy, but you need to tune it to fit experiment and theory together. But what is more reliable is this distance. Yeah, this one between theory and experiment you should be able, when you analyze these distances, you should be able then to define where is your FMR and where is which mode. Okay? So I made a little detour to discuss you now, because I jump here to this point of, so this is longitudinal mode, transversal mode, yeah, and that's what I have shown from Stefan Klinger. It was something else, it was thickness mode. So you can have on top third type of mode, therefore don't be surprised if you see many such nice mode in your experiment. Now coming back, it's critical, as I said, when you have thick yeek and you have standing mode along or perpendicular. But then this case of widening might be less important. So there is a paper, actually I need to find it, but I heard that there's a paper of Resende, who has shown that if you do FMR and you put your sample in a non-uniform field, then FMR line width doesn't broaden. Because if you have one mode which takes all your sample, even if sample is not, this field here and here is different, this mode most likely will create such a special configuration, so it will be not very nice, but its line width will be the same. So line width won't increase. Therefore, be careful. So just check if really there will be broadening of the sample of line width in your case or not. But if you have another situation, like for example, you have, this is your antenna, this is your big permalloy sample, permalloy because propagation L3 path will be of order of 1 micrometer, and you have 1 millimeter long sample, and then you put it in strongly non-uniform field. Of course, there will be no eigenvalue, no single mode across all this, because everything what is excited here propagates only 1 micron. Everything what's excited here propagates only 1 micron. Therefore, more or less, you will measure only here in the place where field of antenna works, and all these parts might be independent. So absorption from this part, so more or less your transmitted signal will be accumulation of all the segments of your sample, because they are not interacting. And in this case, of course, I would expect to have widening. So principally, we are for ourselves just investigating it now. So Andrii Voronov is here, he's simulating it to be sure that it's really like it is. But my message for this lecture course, just keep in mind all these issues, that free path also matters. And you can expect different story from samples with small propagation lengths with large one. Good. Let's move on.
Can I ask one more?
Yeah, sure.
Because we're talking about deep leak now, could you explain why power broadening occurs? Why do I need a glass, for example, as a spacer between my antenna and...
Yes, this I will come in a second, yeah. I have it here. Good, so we discussed why uniformity of the Bayesian field is important, what to pay attention, and my recommendation, if you're experimental, is just check, yeah? So if you have magnet where you can change distance between poles, or you just change position of sample and check if line width is changing or not, then you will see if it matters or not. Stability of Bayesian magnetic field. Usually we use electromagnets. And electromagnets, they have this very fancy power supplies which stabilize your current 10 to the power minus 5, I think, or something. So it means you send 10 ampere and you keep it like at milliampere stability. But keep in mind that your yeek has very narrow line width if you work with yeek. With metals, then you can forget about it. But with yeek, it can have here line width half Oersted. And then you need to check if when you apply, for example, 3 kilo Oersted field, if your power supply with 10 to the power minus 5 stability, if it's smaller stability than this delta H which you expect to measure. Because it might be that in the process of measuring, your peak slightly shifted, and then your line width will be broader. Therefore, keep in mind that also bias in field stability in some cases can be the issue. Temperature stability, especially for YIG, 1 degree gives you Gauss 3-Oersted shift in FMR frequency. If during your measurement temperature was slowing or somebody entered the room and temperature changed 1 degree, this guy will be shifted 3-Oersted, much larger than it is here. Therefore, temperature stability for very sensitive issues also might be an issue. Fix your cables. So what does it mean here? You see in this formula of caloricals there is a reference sample. The point is the following. When you measure this absorption in thin sample, your signal will be principally sitting somewhere in the noise level. Therefore, what you need to do in this case, you should always subtract reference. How do we subtract reference? It's either you have your setup, you measure all the same, but without applied field, with zero applied field, and then you measure more or less this curve. All these troubles here, yeah, so there will be some peak, something like this. Then you measure all this part. It should be the same. And then you subtract from your useful signal, which keeps FMR, you subtract this blue guy, and then you can go to sensitivity of 0.01 dB or something like this. Very sensitive signal. How to take this reference signal? As I said, usually often people take zero value, but my recommendation would be just detune field slightly, because your YIG and GGG, it can change a bit of, it has a complex mu also, and it will change electromagnetic properties of your strip lines. Therefore, what we want to do when we usually perform careful measurements, we just slightly change field, I don't know, 50 millitesla or 20 millitesla, when you shift this peak just outside to make sure that nothing changes, so this background stays the same. And then you take a reference and then you subtract. And then you put your signal field back to this position. You have two signals, and then you can use this formula with reference and this peak in order to subtract one from another. Why I have written about cables? Because cables, even if you buy good cables which is phase stable, little bend in cable will result in phase accumulation. Therefore, after you constructed your setup, please make sure that you put as much as possible Scotch tape or so and fix your cable, or use simply cable which is half rigid. Because if in between measurements of signal and reference you touched cable even a bit, most likely there will be phase accumulation and your feet won't work anymore. Therefore, fixation of cable also important practical advice. Check if you have magnetic components. Yeah, so majority of micro instrumentation which we buy, it's not magnetic, but if you will take any usual SMA connector, if it was, you bought it for 50 euro, then most likely its internal part is covered by some micron thick nickel, which is magnet. And it means that on top of all this, trying to measure here like nanometer thick YIG, you on top have very broad, very strong FMR from microns, from much bulkier, much bigger magnetic layer. So principally you see it only like a shift in offset, but this shift has phase also. Therefore, it might make your life a bit more interesting. You might not notice it in majority of the cases, but sometimes you really see this contribution, particularly in the phase. Therefore, of course, if you want to perform a pure experiment, try to find non-magnetic components, which are immediately 10 times more expensive. So free path of spin waves, and if you have standing mode, so you don't have, check this for yourself, that you understand what to expect from your measurements. We discussed that. Sensitivity of the measurement, so how small sample you can measure. It's given by several factors. First of all, your strip line. For example, pretty often people use not a strip line but CPV. And moreover, our studies show that sometimes CPV is even getting narrower. I think in this company of Johann Ackermann, they do this trick. They make CPV narrower and in such a way they concentrate magnetic field created by the CPV stronger. So you put your sample in the narrower part and you increase sensitivity. So their structures are this cool piece of engineering I can recommend. We also use them. They give you very good sensitivity. I just don't remember how company names, but from Sweden you can find it. And second, what gives you sensitivity is volume of magnetic material. So it means the larger sample, the larger the space it covers in the strip line, the more absorption you will have. And also saturation magnetization. So it means that metallic samples like permalloy, cobalt, iron, boron, Heusler materials and so on, which have large MS, they of course will absorb more power than yttrium iron garnet, which has very small magnetization. Yeah, therefore, what is realistic? So, principally nowadays, with the standard strip-line approach, people measure, I don't know, a few nanometers thick metals and 10 nanometers thick YIG. It's possible to measure. Good. Isolator metallic film. Also keep in mind, so because you have this microstrip and it's metal, and then you put sample on top. And it means that at this part, your sample is metallized and the rest it's free. And some samples like permalloy, it's metal, then you also will have here electric contact and so on. Some cases like yttrium iron garnet, metallization is not important. It's kind of electric contact it's not of critical issue for it's not critical issue for you, but what is important that the metallization changes damping, it might change damping. Therefore, simply your damping on the metallized part and here might be different, not necessarily, but might be. Also think if you want to put some insulator layer in between. Overcoupling, that's what David has asked. So, why do we need a spacer? That's kind of part of microwave, basics of microwave, which I did not add. But principally, if you take resonator, like this resonator, yeah, just a metallic box, in which you excite standing wave using such a loop. So you just bring such a coaxial loop and you excite it. You can make this loop bigger, smaller, you can put it in different positions. You can change the strength with which you couple your transmission line, 50 ohm transmission line, just coaxial cable to the cavity. And this is very critical because there is each resonator, it has unloaded Q factor, so it means that there is frequency exactly like any resonator, like FMR. Frequency, and here I don't know, absorption, let's say. There will be some Q0, some eigen line width of this resonator. And principally you want to work always, in the case of FMR, you want to find this one, line width. If now you will create load, this resonator strongly, the load will change quality of your quality factor of your resonator, and this you see as an increase in the damping. It means that your delta H, delta F will increase because it's loaded. And then we're speaking about Q loaded. So principally it's all described in any book on microengineering, I recommend it. And usually people speak about it just as about resonator, but in reality, for us it's important when you perform yttrium iron garnet measurements. Principally, we don't want to measure delta H, then it will be delta F. Yes, and we're coming back to delta H at the end of the day. You don't want to make to measure loaded resonator. You want to measure original one, real eigenvalue. And what people do for this, if you have microstrip line, side view, yes, so 50 ohm, so some spacing and so on. You just put sample not directly on a strip line, but you put some spacer, piece of glass or anything what is transparent for microwave field. And yeah, thickness you need to check, but principally, let's say 50 micron maybe less, maybe more. And if this is your YIG. And then what you do, you just check if your signal, if it matters for you, because it also depends on many different factors. For experimentalists, it's always easier to check rather than to calculate. What you do, you just put your YIG directly on strip line, you see what is the valence. Then you put some spacer, you decrease load, you unload at your resonator and check if your line is become narrower. And then you put more and more spacers until you see if this is a problem in your case, and your line width should become narrower and narrower until it comes very close to the original one, and then placing more spacers changes nothing in your system. That's what I would recommend, at least. Does it answer your question? Yes. Yeah? Okay, good. Let's see what else I have added to the list. That was about overcoupling. Low temperature measurements. A separate, very fun story. David knows, and Rostislav knows. Keep in mind on your substrate, because substrate is like if it's yttrium and garnet, then it's gallium gadolinium garnet will be a substrate most likely, and this one is paramagnetic, and it works perfectly at room temperature, but as soon as you cool it down and you apply magnetic field, you magnetize it, and it creates a lot of fun for you in terms of damping, position of FMR lines, uniformity of the field, and so on. Therefore, at low temperatures, pay attention. Moreover, you will get troubles with taking a reference signal, because as I said, you need to take reference, this blue guy, for detuned field. And in the case of low temperatures, even small change in field changes strongly properties of substrate, this response, and this blue line is getting larger. Therefore, error bar increases immediately when you work with small damping, with paramagnetic substrate at low temperature. Yeah, and this we discussed. Yeah, when you fit data, always pay attention that you're working in dB or power ratios. Then it's, don't just make formal mistakes. I suppose so much for today. Other questions? I don't see question. Simon, you are measuring YIG sphere, yeah, FMR. I didn't discuss, you're not. Richard is measuring. Okay. Yeah, so how to measure sphere is a separate story. It's easy to do in the resonator. When you put it on the microstrip, then excitation field will be non-uniform. I didn't discuss excitation field, because field created by this microstrip, it's not uniform. Yeah, in ideal case, it should be placed your sample in uniform excitation field, like in cavity. In reality, not. It's there will be microstrip or a CPV or something. In some cases, this non-uniformity of field allows you to excite all these higher modes even more efficiently. Yeah? Therefore, also if you want to fight with them, then think how to make your excitation field more uniform. Yes?
Because I guess one or two lectures before we discussed that we can't transmit a high frequency signal through a signal line. You need a CPV or coaxial cable.
Yes.
How is this then possible with this strip line? Is it just because it's so short, or? No.
So the question is, how is it possible to send microwave signals through the strip line? Because it's it's a strip line proper one, and as I have shown, this is a side view of the strip line on which we put sample. This is a side top view, and this is side view. But you see here is metal, and here some thickness of dielectric. So we always have current flowing in one direction here, and in opposite direction in Yeah, but that's a very good question and very important point, that keep in mind that you need to have proper strip line. Not only that you always have two currents run in the opposite direction, but also that you have characteristic impedance 50 ohm, that everything then works good. Otherwise you will have strong reflection, and you won't be able to perform proper measurements, because majority of microwave signal will be simply reflected.
But for CPV, I would not need it.
You can have both. There is CPV with this ground, and there is CPV without ground. Yeah, not necessarily. You can do without ground. Other more questions? If it's not the case, then thank you very much for your attention.